Welcome everybody, and I'm happy to welcome you back again to our next session of the Digital We Days. My name is Markus Eberle and I will moderate this session today, and I'm very pleased to welcome also our speaker today, Óscar Ciordia, because we are having a joint webinar today with our partner company KDPOF. As already said, Óscar Ciordia will do the presentation today. He's the speaker and he's working as a marketing and sales director at KDPOF. Just a few words before we start into the presentation. You will be muted during this session today. This means that you cannot ask us questions via the microphone, but you have the opportunity to ask us all your questions with the Q&A function, and you will find that in the WebEx control panel on the lower right-hand side. We will go after the webinar through the questions, so the webinar will take about 30 minutes, and then after that we have scheduled 10 to 15 minutes more for your questions. And if we are unable to answer all your questions within this time, we will answer them later on via email. And if you have any emails left after the webinar, just email us at digital-v-days@we-online.com. So then I think it's enough said from my side. At one point, you will also get the link to the presentation as well as to the recording from us by mail later on. So I think in the next few days. And also you will find all that information on our homepage. Now I'm finished. Thank you very much. And I'm happy to give it over, Óscar, to you, and enjoy the webinar.
Thank you very much for the introduction, and thank you very much to Würth Elektronik for giving us this opportunity. It's really, we are very proud to partner with Würth in presenting our technology. We are close partners of Würth. All our reference designs for our ICs really recommend the Würth devices. So again, thank you very much to everybody. I've seen also that we have quite a big audience here. I already recognize several names. Michael, hello, and also Vimali, I see you over there. So hello everybody, thanks for attending, and I hope that this will be a novelty for you, all the things that we will explain. So let me share first my screen with you. So is it currently seen, I guess? Okay, so today I am going to explain to you, or to present to you, the optical multi-gigabit technology for automotive, which is a new technology. It has been standardized very not a long time ago this year, which I think it will be new for all of you, or most of you. Well, I think this has been already shown. The key here is that if you have any questions or answer, please send to them through using the WebEx tool, because I think that will be the most interesting part, which will be your questions. Okay, so just very briefly, I will touch on the company presentation, and then quickly moving to presenting you this new optical multi-gigabit technology aimed for harsh environments in general, and in particular for automotive. And finally, just the flavor of when will you be able to find those this new technology into the market. So very briefly, first about us, about KDPOF. We were founded in 2010. We are located in Madrid. We are around 50 people, most of them working from Madrid, but also we have people in France and some other parts of Spain. We are a fabless ASSP vendor, so we design and we market our products, but we manufacture them in external companies like TSMC, for example, or we package in ASE. As said, our headquarters are in Madrid in Spain, also from people from other locations, and we have commercial offices in places where typically the OEMs are close, car OEMs, automotive OEMs like Sweden, Germany, Japan, Korea, or Great China. So what do? We are IC designers. We are experts in digital, AMS, and also optoelectronics and optic design. We are capable of characterizing ICs and also photonic devices and the qualifications needed for automotive, as well as do some failure analysis on the non-existent failing parts. We have several patents on the key parts of our designs. As you can see over here, we belong, or we are active members of the main associations related with communications in automotive, like JASPAR in Japan or Open Alliance in the rest of the world. We have led the development of key standards, like, for example, the IEEE, which is the standard we will be talking today, but also at European level at ETSI or at the worldwide level at ISO. Our key products are transceivers for optical communications, but also the components of the transceiver. We also sell them separately, like TIAs, transimpedance amplifiers, or LED drivers, and also fuel of optical front ends. As I say, we manufacture in the big manufacturers all over the world, and our main focus is automotive, although we have also some applications in the home and industrial markets. But let's go to the presentation, which is talking to you about the new technology, the multi-gigabit technology based in optical communications for automotive. So first of all, I want to share with you our view of how is evolving the communications within automotive. And to do that, what we will do is we will picture what has happened in another market that is going in front of the automotive market in terms of development, which is the market of the data centers. So in this graph, you can see in horizontal data rate. Here you can see 1 gigabit per second, 10 gigabit per second, 100 gigabit per second, and in vertical we have the distance of the link. What happened in the data centers is what you can see in this graph. So while the needs for data centers were in this yellow region or orange region, copper was the dominant technology to establish the links. However, in data centers, when the demand either for increased data rates or increased distance push the application in this other white region, data centers adopted optical, and this is what I call optical domain. And somehow the barrier separating one domain from the other was this 100 gigabit per second per meter straight line that you can see there. So this is somehow what we can expect from any market that is increasing their demand of either higher, longer distances or higher data rates. You can see here in this blue point, this is a point that where we are today. Typically with ADAS level 0, level 1, you have cameras streaming 2K, 24 bits, 30 frames per second. This is the point where we are today, and clearly this is dominated by copper. However, as ADAS increases the demands, and you can see here this blue dashed line moving ADAS level 1, level 2, you can see that we are starting already to have applications or needs for connecting cameras where they are already in this white area where the data centers move it to optical. But even if we try to project what will happen in the future with ADAS level 3 or level 4, 5, we can see that this is even pushing even farther into this white area. So somehow this is the way that we forecast things will move in the near future. And you can see on the right here a more detailed view of the different sensors, cameras, radars, displays, or the backbone of the car, how around 2030 this is evolving. And this is not our forecast in this case, this is coming from estimations from the IEEE. So, of course, copper can withstand these points here, but of course, this will be with consequences. And the consequences of trying to keep copper also in this white part are the following one. You can, of course, increase the capabilities of copper, adding more parallel lanes. You can also increase the size of the conductors, or the copper conductors, and add even more shielding. You can also increase the complexity of the DSP that you need to equalize or to correct the errors in the copper lines. And of course, you can increase the amplitude of the copper signals, of the voltage signals. With all these technicals approach, you can survive in the white regions, but with the pain, which is, of course, like increase cost and weight of the cables, increase the connector size, decrease the mechanical flexibility of the cables, or increase the power consumption or the latency of the link, and what is even worse is also increase the electromagnetic compatibility issues. So all these forces are the ones that are going to push the copper really to give the way to optical communications in this white area that I was mentioning before. This is a typical application where all these increased demands for communications are coming. You can see that every year, cars are becoming more computers with wheels and sensors connected, and everybody's already talking about the software-defined car, and this is a very typical car in today's days. You can see that you have a lot of connections. You have ECUs, big ECUs interconnected with sensors. You have demands for different speeds, but sometimes those speeds are, as I explained to you, on the white part of the graph. Okay, and again, just relying on electrical has a lot of problems. Problems that you can see here on the right. This is a typical camera to ECU connection based on copper cables, and because of the ground interactions of this harness, you have problems like attenuation, EMC, electrical noise, and problems of galvanic isolations. All these problems are completely solved if instead of having a point-to-point link based on copper, you use is with optical. Of course, every engineer will tell that you can solve these problems. Of course, you can do that, but why try to solve a problem if you can completely get rid of them? That's the wise way to do that. But of course, automotive requirements are not easy, are hard. And before, when the task of developing a new standard for multi-gig communication in automotive, we had to take into account all these requirements. So the typical requirements for automotive, you have them over here. In terms of reliability, they require better than 10 failure in time fits over 15 years of lifetime. You need to pass a strict qualification plan outlined in the AEC-Q 100 standard. And in our case, in the case of these chips, these ICs, they require to be grade 2, which means that the environment temperature where those need to be functioning is -40 to 105 degrees Celsius environment temperature. Also, we had very strict demands like a certain IC package pitch and soldering requirements, the type of connector housing, the IC mating. Also, in terms of the cable and connector, although we are not providing the cables and connectors, but this kind of performance requirement is also set or established in the Ethernet or the IEEE new standard, and things like the bending, the vibration, the chemical loads that those cables need to support are also very clearly set up. And finally, the optical parameters like the emission profile, wavelength, or optical power that you need to supply in all these environments and during the lifetime is clearly stated as well. For example, it's clearly stated that we need to support 40 meters length with 4 inline connectors. So with all this, it was set up a task force in IEEE, in the IEEE organization, to come up with a standard, and it was published in 2023, and this standard, that is 802.3 CZ. For those that are not familiar with this, this is basically stating that the Ethernet, which in general is 802.3, has an amendment, a new part, which is the CZ part, which is the one that we are talking today. It specifies a new physical device for automotive applications, supporting data rates between 2.5 and 50 gigabit per second in a single lane. It should be committing to or passing the ACQ 100 grade 2 of operation. In this case, it's stated as junction temperature, not ambient temperature, between -40 and 125 degrees, supporting a maximum of 40 meters, so that applications not only in cars but also in buses and trucks can be supported, up to a maximum of 4 inline connectors, supporting also diagnosis, wake up and sleep functions, and dependability functions, and also, and this is very important, a PHY that supports energy efficient Ethernet. This is key to ensure that applications, for example, camera connections, cameras are very small in automotive, and they are very much constrained in terms of the heat that they can dissipate. So having a PHY chip that is low power or can operate in a low power mode is key to meet the demands. So this was specified, and all this was also specified using or not inventing new fibers or new light sources or no new photodiodes, but actually this standard specifies that the fiber has to be of the type OM3, which is glass fiber multi-mode 125 microns, which is the currently used in the world in millions and millions every year. Big cells, 918E big cells, which are also big cells well known in the manufacturing industry of big cells, and photodiodes as well. So by using this or leveraging these components, you ensure that at the end your final port will be a very affordable one. This is just showing one of the big problems that you can see in copper, and one of the reasons that optical makes sense. In this case, you can see in horizontal the frequency, in vertical the insertion losses of a point-to-point link. In this case, is a point-to-point link made in copper, and you can see that there is a notch here. Well, when the cable was originally manufactured, is a red line, so you have, of course, a change of the insertion loss with frequency, but also when the cable is aged, you can see this deep dive in the insertion loss curve. Whereas in the optical thing, you can see here the green line in horizontal, where basically there is no change. So just by seeing this graph, you can understand that the solution based in optical in terms of the transceiver itself is going to be much simpler, because you don't need to equalize or to do nothing special, and this translates into a shorter latency, cheaper component, and low power consumption. I won't go into the details of this. I just wanted to put this table so that you can check yourself the details of the optical PHY compared to the copper PHY, and you can see in this table what I have said before in terms of complexity, power consumption, and other parameters. The device itself will be very simple. It will be a single device. This is the device, how the device looks from the upper part. From the lower part is a simple BGA component that you can solder in a regular reflow process, and inside the component you will have three bonded ICs: the main CMOS die, a big cell, and a photodiode. So everything together will be the component that will be soldered and connected to the optical line. Inside the component, you can also go in, I won't go into the details, but you will have the digital part with all the different interfaces, Ethernet and camera interfaces, and also the driver, pixel, photodiode, everything on the same die, and then the pixel and the photodiode bonded into the same substrate. This is what is specified in the standard. Then on the top of the component, obviously I'm not showing here the real component because it's still confidential, it's under development. On the top of that is where you insert the connector and then plug in the fiber. This is just showing how there is a huge reduction in terms of the size of the port. The upper part here is showing the 1000 basically one port, the copper port. In the lower side, you can see how would the port look like in the case of optical. So you can see a huge reduction also in terms of size. I put for your reference a couple of examples of proof of concepts that are currently undergoing in OEM and Tier 1. This is a proof of concept that we are doing with a big OEM in the US, which is linking several radars with a central image processor computer. And all these links are made using fibers at several gigabit per second. In this other proof of concept, in this case, what we are linking is several cameras with a central ECU. We have evaluation boards already where in this evaluation board it's basically a media converter between optical and copper, and it's the vehicle that we are using to demonstrate the technology in any interested party. Just to finalize the roadmap, we will release 3 waves. The first wave will be the first wave. We will be sampling this mid next year, although, as I told you before, we are already demonstrating the technologies with the evaluation boards, but the sampling of the ICs will be mid next year, and the SOP will be mid 2026, and this wave will be covering up to 12 gigabit per second. In the second wave, we will push and cover 25 gigabit per second, and the wave 3 finally in 2030 will be covering 50 gigabit per second. As I am showing here, the standard covers up to 50 gigabit per second, but, and this is important, the fiber and the connectors are capable of 100 gigabit per second. So thank you very much for your attention. That's pretty much my presentation. There is more information in the handouts that you can check later on, and will be open to any question. Thank you.
Okay, so now I'm back. Óscar, thank you very much for your presentation. So yeah, now, as you said it's time for the questions. So we will go directly into your questions. As said in the beginning, you can send us all your questions with the Q&A function. You will find that on the lower right-hand side of the WebEx function or WebEx panel. So yeah, let's quickly start into the questions. Óscar, first question. What is the current status in regards to the speed of the links in the cars? And also the second question here, what are the driving forces behind the increasing demand for higher speeds?
Yeah, thanks for the question. So yeah, as I mentioned, the drivers for the increasing demand of high speeds in the cars are the different sensors that are connected to the central ECUs, and also the backbone that connects big ECUs within the cars. That's the big demand, or is the driving forces. In terms of where are really the technology now, cars are already implementing 1 gigabit per second links. And there is starting to be models of cars that probably will be released next year with some 10 gigabit links for the case, for example, of linking the event data recorder, the so-called black box, with the central ECU. For this specific link, you need 10 gigabit, but again, will be very, very few and in very high class cars.
Okay, so Óscar, thank you very much for the answer. Then yeah, let's jump into the next question. How is the optical fiber perceived in the automotive industry, and aren't they afraid of adopting it?
Yeah, that's an excellent question. The first reaction that you always have when you go to an OEM and tell them that you propose this technology is like, "Wow, we are afraid. Optical is fragile. It breaks." And you know, and of course, if you don't you don't go into the details, yeah, the glass optical fiber use is the same as the use, for example, for the fiber to the home. But there is a big difference, which is the cable. The cable that you make with the core of this fiber has several layers that reinforce it. So at the end, the fiber that you get for automotive is a fiber that you can bend it, you can do crazy things with it and without breaking that. So when we show them to customers, we demonstrate to them and let them play with the fiber, they realize that, of course, you need to go into the details of what optical fiber you are using to realize that this is completely safe and reliable for automotive.
Okay, thank you very much, Óscar. I see one more question. Maybe just before that, just the information for all of you. You will get the presentation as well as the link to the recording from us by email in the next few days. So you can download all your needed stuff then, or the needed material. So then, yeah, let's go into the next question, Óscar. As speed grows, will the fiber and connectors need to change along with the transceivers, or will they keep the same?
Yeah, that's another good question. That's a big advantage of this technology, which is that the fiber and the connectors that you use, let's say for the minimum speed of, let's say 10 gigabit, will be exactly the same as up to at least 100 gigabit per second, if not more than that. So an OEM or a tier one that adopts this technology, they will need to qualify the fiber and the connectors just once. And probably this will be the same for the next, I don't know, 10, 15, 20 years, which is something that does not happen with copper, where going from 1 gigabit to 10 or from 10 to wherever if there exists something, cable and connectors will be different. So that's a big advantage.
Okay, that's nice to hear. Thank you, Óscar, very much. For now, that's was the last question. So yeah, I think that's also a good sign when every question is answered already. So yeah, everything was in the presentation. So thank you very much, Óscar, for your time today and your presentation.
Thank you very much to you. Again, thanks to Würth. And any question, please send me an email and I will be happy to answer that.
Yeah, perfect. So then yeah, we are finished with this session. I hope you stay tuned and maybe, yeah, join the next webinar session of our Digital V-Days. And I'm, yeah, happy that you took the time to participate. Thanks for your attention, and I wish you a good day. Thank you and goodbye.